Welcome to the fourth lecture on C-star algebras, titled Representations of C-star algebras. We have seen that any C-star algebra is star isomorphic to a closed, self-adjoint algebra of continuous linear endomorphism of a Hilbert space. This observation follows from the GNS construction, which we now recall. Let's fix a unital C-star algebra. If phi is the state of the C-star algebra, we can define a pre-inner product on the C-star algebra by setting for all A and B that the product of A and B is phi of A star B. Then we can use the process of separation completion applied to the C-star algebra with this pre-inner product to get a Hilbert space L2 of phi. And we have, of course, a canonical map which to any element of the C-star algebra maps its class in L2 of phi. We then can define an action of the C-star algebra A on that Hilbert space by setting phi of A applied to psi of B equal psi of AB for any A and B in your C-star algebra. And it's easily checked that indeed we thus have defined a unital star morphism pi from the C-star algebra to the C-star algebra of bounded operators on L2 of phi. Moreover, there is a special vector omega in the Hilbert space L2 of phi, which is the image by psi of the unit of the C-star algebra, and has two properties. First, you can recover phi of A, where phi is the state we started with, as the inner product of omega with phi of A applied to omega. So we can recover naturally the state we started the construction with. And second of all, if you look at the subspace pi of A applied to omega for A ranging over your whole C-star algebra, then you simply see that you obtain by construction the image by psi of the C-star algebra, and that is of course dense in L2 of phi. This construction is an example of a star representation. In fact, it's an example of a special kind of a star representation called cyclic representations. A star representation of a C-star algebra on a Hilbert space is a star morphism from the C-star algebra to the concrete C-star algebra of bounded operators on that Hilbert space. We saw that the Gelfand-Naimark-Segal construction is the source of many star representations. Those star representations are in fact of a special kind called cyclic, and we will see in this lecture that all representations can be decomposed into sum of cyclic representations in a specific sense. But first, we want to discuss a notion of equivalence between star representations. We already know what it means for two C-star algebras to be isomorphic. Now we turn to the question of what it means for two Hilbert spaces to be isomorphic. The proper notion of isomorphism for Hilbert spaces is called a unitary. A unitary is a linear surjective isometry from a Hilbert space to another one. Because unitaries are such an important concept, we're going to study them a little bit more. First, I'm going to show to you that a map U between two Hilbert spaces is a unitary if and only if it is a surjective isometry which maps the zero vector to the zero vector. So linearity is essentially for free if we are working with a surjective isometry mapping 0 to 0. To prove this, let U be a surjective isometry which maps the zero vector to the zero vector. For any vector h in the domain of U, the norm of U of x equals to the norm of U of x minus U of 0, since U of 0 is 0. But that is a distance between U of x and U of 0, and since U is an isometry, that equals the distance between x and 0, which is the norm of x minus 0, or simply the norm of x. So, the map U must preserve the norm. As a consequence, using the polarization identity in our Hilbert space, we get that U must actually preserve the inner product, that is, for any x and y in the domain of U, the inner product of U of x with U of y equals the inner product of x and y. Using this observation, we now prove U is indeed linear. So, to do that, we take x and y, two vectors in the domain of U, and lambda is scalar. And we'd like to prove that the vector U of lambda x plus y minus lambda U of x plus U of y is a zero vector. To do that, I'm going to take the inner product between this vector and a vector of the form U of z for z arbitrary in the domain of U. Using sesquilinearity of our inner product, we can then expand this expression into combinations involving three inner products, all of which are of the form U of a vector inner product with U of another vector. And since u preserves the inner product, as we have just seen, we can, quote-unquote, remove u to get a new expression that does not involve u, and which is then, using this equilinearity of the inner product again, easily seen to be 0. Therefore, since u is surjective, we can apply this result to a specific z in the domain of u, for which u of z equals a vector u of lambda x plus y minus lambda of u of x minus u of y. And then we have seen that the square of the norm of this vector is indeed 0. So this vector is 0, which in other words means u of lambda x plus y equals lambda u of x plus u of y. As lambda x and y were arbitrary in their respective spaces, we can conclude that u is indeed linear. As a linear surjective isometry, u is a unitary by definition. Now, of course, if u is a unitary, then u is a surjection, an isometry, and being linear, it maps the 0 vector to the 0 vector. And so we have shown our equivalence. Continuing with our characterization of unitaries, we see now what is probably the most important characterization of these maps. So let's fix two Hilbert spaces. A map between two Hilbert spaces is unitary if and only if its adjoint is its inverse. To prove this result, let u be a unitary. Thus, in particular, u preserves the norm, and as we have seen, using the polarization identity, u preserves the inner product. So, if we calculate u star u applied to a vector in the domain of u, inner product with another vector in the domain of u, we can move the u star on the other side using the definition of adjoint. And we see that since u preserves the inner product, we can drop u altogether. So we get that for any eta and psi in the Hilbert space domain of u, u star u of psi inner product with eta equals to the inner product of psi with eta. And this means by uniqueness of the adjoint that u star u must be the identity of the domain of u. Now, we have shown that u star u equals u inverse u, because of course u inverse u is the identity of the domain of u. And since again u is invertible, we can multiply this equality by u inverse on the right, and we get that u star equals u inverse. Therefore, we can also conclude that u star is u inverse, and this is the identity on the codomain of u. And here, note that I assume u is invertible. That's why I don't need to calculate u star first to conclude that u is invertible. We already made that assumption. Conversely, let u be an invertible linear map whose inverse is given by its adjoint. Then if psi is in the domain of u, the square of the norm of u psi is the inner product of u psi with itself. Then using the adjoint, this equal to u star u psi inner product with psi, but u star u is by assumption the identity. So this is the inner product of psi with itself, that is the square of the norm of psi. Taking the square root, we get that u is an isometry. It's invertible and isometric, so in particular it is what we call a unitary. Now let's look at an interesting connection between unitaries and the star automorphisms of the C-star algebra B of H of all bounded operators on a Hilbert space H. Again, H here is a Hilbert space, but theta from B of H to B of H is a star automorphism if and only if there exists a unitary of the Hilbert space H, such that for all A in B of H, that is for all A bounded operator of H, theta of A equals u star. So in other words, theta is the adjoint action for the unitary u, or, put differently, theta is what's called an inner automorphism. So we see that the star automorphisms of the C-star algebra of all bounded operators on a Hilbert space are implemented exactly using unitaries of Hilbert spaces. Let's prove this very interesting result. Let theta be a star automorphism of B of H. First, I am going to see what happens to rank 1 projections. So let P be a rank 1 projection. In other words, there exists psi, a vector in H of norm 1, such that P equal to the inner product with psi and input times psi. Now P equals P squared equals P star, since P is a projection. Therefore, since theta is a star automorphism, we also have that theta of P squared is theta of p star is theta of p. In other words, theta of p is also a projection. I would like to know what is the rank of theta of p. Let's suppose, for a moment, that the rank of theta of p is strictly more than 1. I claim that then there exist two non-zero projections, q and q prime, which are orthogonal in the sense that q primes equal q prime q equals 0, and such that q times theta of p equals theta of p times q equals q, and theta of p times q prime equal q prime theta of p equals q prime. To get the existence of q and q prime, we could follow the following strategy. Since the rank of theta of p is strictly more than 1, I can find an orthonormal family of two vectors inside the range of theta of p. Let's call these two vectors xi and xi prime. Let q be the projection on the span of xi, and q prime be the projection on the span of xi prime. Since xi and xi prime are orthogonal, it's easy to check that q primes equal q prime q equals 0. Now, because xi is in the range of theta of p, it's easy to check that theta of p times q equals q. On the other hand, let's say that eta is orthogonal to xi. Then q of eta is 0. But on the other hand, theta of p of eta is also orthogonal to theta of p of xi, which is actually just xi. And that's because p being a self-adjoint, theta of p is self-adjoint. And then we deduce once more that q of theta of p of eta is 0. That is actually enough to conclude that q times theta of p is also equal to q, since of course they agree on the span of xi. The same reasoning applies for q prime, so we have the desired identity with this choice of q and q prime. Now, let R be theta inverse of q, and R prime be theta inverse of q prime. Theta is a star automorphism, so theta inverse is also a star automorphism, and that tells us a lot of information about R and R prime. For instance, R and R prime are both projections, for the same reason as theta of p is a projection, because p is a projection. That is, we can easily check that R equals R square equals R star, and similarly with R prime. Moreover, since neither q nor q prime are 0, and since theta inverse is of course injective, R and R prime are non-zero projections as well. Applying theta inverse, which again is a star automorphism, to the orthogonality relation q primes equals q prime q equals 0, we get that R prime equal R prime R equals 0. So R and R prime, which are two non-zero projections, are in fact orthogonal. And last, again applying theta inverse to the relation between q and theta p, we get that p times r equals r times p equals r, and similarly we get p r prime equals r prime p equals r prime. But then this implies in turn that the dimension of the range of p must be strictly more than 1. And basically it's the same reasoning in reverse. You take xi and xi prime, two vectors of norm 1, with xi in the range of r and xi prime in the range of r prime. Since r and r prime are orthogonal in the sense that r prime equals r prime r equals 0, it's easy to check that the range of R is orthogonal to the range of R prime, and so Xi in particular is orthogonal to Xi prime. In addition, since P times R equals R, you see that when you apply this identity to, say, Xi, you get that P of Xi equals R of Xi, which is Xi. And therefore, P of Xi is Xi, and so Xi is in the range of P. And similarly, Xi prime is in the range of P as well. Then this tells you that we have found an orthonormal family of two vectors inside the range of P, which forces the dimension of the range of P to be at least 2, since of course orthonormal families are linearly independent. Since we know that in fact we chose P as being a rank 1 projection, we can conclude that theta of P must indeed have rank 1. This is a very interesting first quick observation. A star automorphism of B of H maps rank 1 projections to rank 1 projections. Therefore, there exists a normalized vector eta in U-Hilbert space so that theta of P equals the inner product of eta with the input times eta. Now I'm going to apply this observation to a Hilbert basis of my space. So let psi sub j, for j ranging over some index at big J, be a Hilbert basis for my Hilbert space. For each j, there exists an eta j vector of norm 1 in a Hilbert space, such that the image by theta of the rank 1 projection on the linear span of psi j is the rank 1 projection on the linear span of eta j. This eta j vector is not unique. if you multiply it by a unimodular complex number, you get another candidate for the same relation. But let's just pick one of them and call it eta j, and let's define u of xi j to be eta j. I'm going to make some observations about this family eta j I just made. So for two distinct indices j and k, we know, of course, by definition of a Hilbert basis, that xi j is orthogonal to xi k. And therefore, the composition of the projection on the span of xi j with the projection on the span of xi k is 0. That is, the projections are so-called orthogonal. But this is an algebraic statement, but I can apply theta to this relation, and since theta is a star automorphism, I can conclude that the projection on the span of eta j composed with the projection on the span of eta k is indeed 0. And from this, a direct, easy argument shows that eta j must be orthogonal to eta k every time j is not k. So the family eta j, for j ranging over our index set here, is an orthonormal family. We just proved the orthogonality relation, and the vectors are all normalized by construction. Now I want to prove it's actually a Hilbert basis of my Hilbert space H. So let zeta be some vector which is orthogonal to the linear span of all the eta j's. And let's assume zeta is not 0. In fact, if I do so, I might as well assume zeta is normalized. I can then consider the projection q on the linear span of zeta, given by this usual formula. And there are a few things I know about q. I know that q as a projection composed with the projection of the linear span of eta j equals the projection of the linear span of eta j composed with q equals 0. That's because zeta is orthogonal to all the eta j's. But then I can apply the star automorphism theta inverse, and it tells me that theta inverse of q composed with theta inverse of the projection on the linear span of eta j must be 0. But theta inverse of the projection on the linear span of eta j is the projection on the linear span of xi j. So I concluded that theta inverse of q composed with the projection of the linear span of xi j must be 0 for all j. And it's also true, of course, when you commute those two projections. Now, on the other hand, I've also shown that theta inverse of q being a rank 1 projection, is a rank 1 projection because the image by star automorphism of a rank 1 projection is a rank 1 projection. So that means that there exists a vector omega in my space of norm 1 such that theta inverse of q equals the inner product of the input with omega times omega. But what's important about this is simply the observation that this vector omega must be orthogonal to any vector xi j, since theta inverse of q composed with the projection on the linear span of xi j is always 0. And that's a contradiction because we found a vector of norm 1 that must also be orthogonal to all the vectors in a Hilbert basis, but the only vector that's orthogonal to all the vector in a Hilbert basis is a 0 vector. And that means that the eta j family is a Hilbert basis of our space as claimed. Now that we know that, you can take this U that we define here that maps a Hilbert basis to a Hilbert basis, extended first by linearity and then by continuity, and you can easily check that it is, of course, a linear bijection since it maps a Hilbert basis to a Hilbert basis, but it's also an isometry for the same reason, and therefore it's a unitary operator. So we have constructed this unitary operator of our Hilbert space from theta, and specifically from the action of the automorphism theta on rank 1 projections. Then we also make an observation. Now by construction, if you give me an index j, theta of the projection of the linear span of xi j equals to the projection on the linear span of u of xi j, which is eta j by construction. But then it's very easy to see that if you give me a vector xi of norm 1, then that vector xi is in the closure of the linear span of the xi j's. So we have the following relation, that theta of the inner product of xi with the input times xi, which is this particular rank 1 projection, is again equal to u applied to xi inner product with the input times u of xi. This is simply the natural extension, if you want, of the relations that defined u to begin with. But then we can, of course, use the fact that u has an adjoint. So this is equal to this expression here of xi inner product with the adjoint of u applied to the input, the whole thing multiplied by the vector u of xi. And that turns out to be exactly the adjoint action of U on the rank 1 projection defined by xi. So we get the relationship we want about theta, but just on these rank 1 projections. But actually, as we are going to now show, this is all we needed. We can extend the result from rank 1 projection to all the operators in B of H. So to do that, we're not going to use a continuity result. This is tempting, but not quite the right approach. To keep things at this level of generality, we are going to instead make a kind of cute observation. The first observation I'm going to make is that if I take now two vectors psi and eta of norm 1 in my Hilbert space, and I look at this rank 1 operator, it's no longer a projection, but it is still a rank 1 operator, which is the most general form a rank 1 operator can take, which is the inner product of psi with the input times the vector eta, then it can be expressed as a linear combination of two rank 1 projections. And therefore, since theta is linear, when you apply theta to this expression, you get an expression in terms of the linear combination of these images of the rank 1 projection given by the first displayed equation. It's a quick algebraic exercise to check that indeed this equals U times this rank 1 operator times U star. So the relation extends to rank 1 operators just by linearity, and a quick calculation I'll let you do. But now that we have this observation, we can actually conclude our theorem. And it's just an algebraic trick. So let A be in B of H and let psi be a vector of norm 1 in your Hilbert space. Let's calculate U applied to A applied to psi. Now, the trick here is to observe that psi is the image of itself by the projection on the linear span of psi, which is what I wrote here. I mean, it's a trivial observation, since after all, psi has norm 1. But the reason why it's a nice observation is because I can actually calculate what A times this projection is, and a quick calculation shows you that it becomes a rank 1 operator given by this expression here, the inner product of psi with the input times A times psi. Okay? So this is simply putting A inside the projection, using the usual algebra. But then on the other hand, I'm here cheating a little bit. U is a unitary operator, so I can insert U star U just before the last vector psi at no cost because U star U is the identity. So we did two steps here. We calculated A times the projection on the linear span of psi as this rank 1 operator, and we inserted U star U just before the vector psi. Since U star U does nothing, it's the identity. But then look at the first three factors in this equation here. We've just shown that U times a rank 1 operator times U star is theta of that rank 1 operator. We write this. And, well, we're left with U times psi, which did nothing. But then we can kind of unfold our computation because psi inner product with the input times A times psi, well, just like before, is A times the rank 1 projection on the linear span of psi. So in other words, I simply undo what I did between the first and the second line here. But then theta is the star automorphism, so it's multiplicative. So I can split my calculation here as theta A times theta of the rank 1 projection times U of psi. Then what is theta of this rank 1 projection? Well, it's again this rank 1 projection conjugated by the unitary U. And then you see again the U star U cancel. And then you simply see that we're applying this projection on the linear span of psi to psi, so we get psi. And so you simply have shown that indeed U times A times psi is theta A times U times psi. And therefore, since this is valid for any vector psi of norm 1, it's easy to prove using linearity that it is valid for every vector in your Hilbert space. So we have shown that U times A equals theta of A times U. And then, since U is unitary, that tells me that UA U star is theta of A. And we are done with our proof. And the converse is immediate. If I give you a unitary U, you can simply check that the map defined by add U, as in the theorem, the adjoint operation of U, is indeed a star automorphism. That's very, very easy. So we have a complete description of the star automorphism of the bounded operators on the Hilbert space in terms of unitaries, which gives us another reason to believe that unitaries are the right choice of isomorphism for our category of Hilbert space. Now, armed with this understanding, we can actually discuss equivalence of representations in, I think, a reasonably convincing way. So let's say that we have two representations, pi1 and pi2, of some C-star algebra. And let H1 be the Hilbert space on which pi1 acts, and H2 be the Hilbert space on which pi2 acts. And I would like to know what it means for those two representations to be essentially the same. And one natural idea would be, well, there exists a star isomorphism, rho, from the C-star algebra B of H1 to the C-star algebra B of H2, such that rho composed with pi1 equals pi2. That is, in other words, when you give me an element A of my C-star algebra and you calculate pi2 of A, that's some operators on the Hilbert space H2, but that operator could be obtained by plugging the same A inside of pi1, which gives me an operator on H1, and then bring it to an operator on H2 by the star isomorphism rho. And having a star isomorphism means that, of course, you can invert its relation, so it's certainly symmetric. It's trivially reflexive using the identity star isomorphism, and the composition of star isomorphism being a star isomorphism, it's also a transitive relation. And it's basically saying that though pi1 and pi2 technically are star morphisms from A to different C-star algebras, B of H1 or B of H2, those two different C-star algebras are actually the same in the sense that they are star isomorphic. And indeed, those two star morphisms, pi1 and pi2, are conjugate to each other through one of the isomorphism between B of H1 and B of H2. So that's a very natural notion of saying when these two maps are the same. But we've just seen that star automorphisms of B of H are implemented by unitaries. And from there, it's actually fairly easy to see that star isomorphisms are also implemented by unitaries. It's a very easy exercise. And therefore, we have the natural following definition. Two star representations, pi1 and pi2, on two different Hilbert spaces, respectively H1 and H2, are unitarily equivalent when there exists a unitary U from H1 to H2. So remember, a linear isometric projection, such that for all A in the C-star algebra, U pi1 of A U star is pi2 of A. In other words, we can conjugate one representation into the other using a unitary. Again, since it is exactly the same notion as the one using star isomorphism above as we discussed, this is trivially an equivalence relation. It can also be checked immediately since the product of unitaries is again a unitary. So we have now a notion of what it means for two representations to be, for all intent and purposes, the same. That's an important concept. I'm going to move toward an application of this notion of unitary equivalence when I discuss cyclic representations, but I'd like to first clarify a point of terminology, because the word unitary is kind of used in two slightly different contexts, but of course very tightly related. So if A is a unital C-star algebra, an element U of A is called a unitary of A if U star equals U star U equals the identity. So again, if and only if U is an invertible element of your C-star algebra whose inverse is given by its adjoint. And we've seen that certainly if A is B of H for H a Hilbert space, then in particular, unitaries from the Hilbert space to itself are exactly unitaries in the C-star algebra B of H. We have shown that. But the relation is a little bit more complicated if, say, we want to talk about unitaries from a Hilbert space to another Hilbert space. What happens here is that, well, there are two things you can do. You can simply decide once and for all you identify the two Hilbert spaces and move on. Then you're really just talking about an element of, again, the C-star algebra B of H being unitary. Or you could say I want to keep them different for some reason. And then there is another way to understand that a unitary in that sense, that is a linear isometric surjection between Hilbert spaces, is indeed a unitary in the C-star algebraic sense. And the way to do it is to consider that your unitary is a particular unitary of the C-star algebra of bounded operators on the direct sum of the two Hilbert spaces. So with this in mind, let me make a quick series of observations about unitaries in a C-star algebra. If U is unitary, then of course U is normal, as stated in the definition, since clearly it commutes with its adjoint. We can calculate the norm of unitary, and if U is a unitary, then the norm of U, of course, is the square root of the norm of U star U, because this is a C-star identity. But U star U is the unit, and the unit in a unital C-star algebra always has norm 1. So the norm of any unitary is 1, and in fact, we can do a little bit better than this. Since U is a normal operator, we can look at its C-star algebra generated by U in the unit, and we know we're going to get an abelian C-star algebra, and we can look at its spectrum. But we know that the Gelfand transform, which map U to the identity once we do the identification between the Gelfand spectrum and the actual spectrum of the operator, is a star automorphism. So what it tells me is that the identity multiplied by the conjugate of the identity over the spectrum of U is always equal to 1. That forces the spectrum of U to be made of unimodular complex numbers. So the spectrum of a unitary is always a subset of the unit circle and the complex numbers. It's easy to also check, again using the same properties of the Gelfand transform really, that if you have a normal element whose spectrum is a subset of the unit circle, then it is in fact a unitary. That characterizes among all the normal elements which one are unitary. So a consequence of that is you can actually make a lot of unitaries in a unital C-star algebra, because if you take a normal element and you simply apply to it a function whose range is a subset of the trigonometric circle, and that function is continuous on the spectrum of A, whatever that is, then f of A is unitary, because it's normal and, as we have seen, has the spectrum that it needs to have for this conclusion to hold. So certainly, since there are a lot of normal elements and there are a lot of normal elements with non-trivial spectra, and you can find a lot of continuous function from those the spectra of those normal elements to the trigonometric circle, then we have an ample collection of unitaries in a unital C-star algebra. Another quick observation is that if you look at the set of all the unitaries in a unital C-star algebra, then it's a closed subgroup of the group of invertible elements in your C-star algebra. Last, let's relate this notion of a unitary of a C-star algebra to the notion of a unitary between Hilbert spaces. To do that, let's remember that we can make Hilbert spaces out of C-star algebras using states. So let phi be a state. I'm going to look at what happens if I pick an element A in my C-star algebra. I look at it as a vector in L2 of phi, and I would like to know if U acting on that vector it actually preserves the norm of that vector. And it's easy to do because we just calculate that the pre-inner product of UA with UA in the sense induced by phi is phi of A star UA, and the U star U in the middle becomes the identity. So it's phi of A star A, which is indeed the square of the norm of the vector A in L2 of phi. So you see that U is an isometry of L2 of phi in the GNS construction. So any unitary of the C-star algebra is indeed acting as a unitary in any of the Gelfand-Naimark-Siegel construction of a C-star algebra, and we'll see in a moment, therefore, in any representation of the C-star algebra. So this is in that sense that the two terminologies are now reconciled. So I'm now going to use my notion of unitary equivalence to discuss a decomposition result. So we have some special representations, the GNS representation. And, well, we know that they're interesting, but now we're going to see that they are in some sense fundamental because they are the building blocks for any other representation. So first of all, I'm going to study what I call cyclic representations, which are the representations that look like GNS representation and in fact, as we are going to show, are unitarily equivalent to GNS representations. So a star representation pi of a C-star algebra on a Hilbert space H is cyclic when there exists some vector in H, let's call it psi, such that pi of A applied to psi, where A ranges over your whole C-star algebra, is a dense subspace of the Hilbert space H. So basically, you take one vector and you move it around any way you can using the C-star algebra A and the representation of A on the Hilbert space, and you get, well, not necessarily everything, but at least a dense subset. And this is a very natural notion in view of what we did with GNS constructions. A vector psi that has this property is called a cyclic vector for the representation pi. And of course, it is never unique unless you're talking about the trivial situation where we're acting as zero everywhere on the Hilbert space 0. And the theorem that's very important is that if pi is a cyclic representation on a Hilbert space with some cyclic vector omega that I'm going to assume is unital, normalized to norm 1, note that again, if it's 0, then there's nothing interesting to say, then setting that for all A in your C-star algebra, phi of A is the inner product of omega with pi of A applied to omega, then this phi is actually a state of your C-star algebra, and your representation, your cyclic representation, is actually unitarily equivalent to the GNS representation for that particular state. So another way to state that is a representation pi is cyclic if and only if it is unitarily equivalent to the GNS representation for some state, since we know that GNS representations in particular are always cyclic. I'm going to prove this result. I keep the theorem on top of the slide here. The first thing I need to show is that this definition of phi gives me a state. It's trivial that phi is linear. That owes to the sesquilinearity of my inner product. So now, in order to show that phi is actually a state, I'd like to prove it as norm 1, and it is a positive map. And we know that to do that, one thing we can do is show that the norm of phi is 1, but it's also equal to phi of the unit of the system algebra. That's one of the characterizations we have about positive linear functionals. So I'm going to use that. So first of all, what is phi of 1, phi of the unit? Well, you just look at it. You plug in your representation pi of 1, and pi of 1 act as the unit, so you get that phi of 1 is the square of the norm of omega, which is 1. But on the other hand, by the Cauchy-Schwarz equality, phi of a in modulus is less or equal than, well, the norm of omega times the norm of pi of a times omega. But then the norm of omega is 1, and pi of a times omega, the norm of that is less or equal than the operator norm of pi of a applied to omega, again, having norm 1. And last, since pi is a star morphism, we know that the norm of pi of a is less than the norm of a. So we have shown that for any a in your system algebra, the modulus of phi of a is less or equal than the norm of a. And therefore, since this is reached at 1, phi is indeed a state. It has norm 1, and that's equal to phi of the unit. So now that we have defined a state, why is the representation pi equivalent to the GNS representation for this state? And this is just a little quick check, because what you want to do is define a unitary which somehow intertwine the two representations. Pi, the representation we started with, and what I'm going to denote again by pi sub phi, which is the GNS representation obtained from phi. And we have this cyclic vector. That's very important. So omega is a cyclic vector for pi, and then we had this cyclic vector for the GNS representation. So take an element A in your system algebra. You can apply pi sub phi at A to the cyclic vector of the GNS representation, gives you some vector in the Hilbert space L2 of phi. Or you can apply pi of A to the cyclic vector omega. And what I want is simply that basically my unitary that I'm looking for maps one to the other, as stated here. And this is enough to define actually a unitary. The reason is because by assumption omega is cyclic, we know that we have defined U on a dense subspace of our Hilbert space. And it's very easy to check by a computation I do at the bottom of the slide here that the map thus defined on that dense subspace is actually isometric. Preserves the norm. It's linear. Therefore, it has norm 1. It extends to the entire Hilbert space by density to a unitary. And it is then by construction that it is intertwining the two representations. The only thing you could be worried about in this first displayed equation is it well defined? Could I have that technically pi of a of omega equals pi of a prime of omega? That is, when I act on omega by two different elements of my system algebra, I get the same answer. But somehow when I act on the GNS side, I do get different answer. And the answer is no. And that follows from, again, this isometric property. Because if it is the case that pi of a omega equals pi of a prime of omega, then pi of a minus a prime to omega is 0. And as we see, that then implies that pi sub phi of a minus a prime applied to the cyclic vector for the GNS representation must have the same norm, which is 0. And therefore, pi phi of a applied to the cyclic vector of the GNS representation equals pi phi of a prime times the same vector. And so there is, in fact, no problem of well definition. This is a well-defined map U. It does extend to a unitary as we wanted. So now we can conclude that cyclic representations are in fact the building blocks of every representation of a system algebra. Therefore, by unitary equivalence, GNS representations are the basic building blocks of any representation of a system algebra. So here's the main theorem. If pi is a star representation of a unit or system algebra on some Hilbert space H, then the theorem says I can decompose H as an orthogonal sum or Hilbert sum of Hilbert subspaces as follows. You can find a subset E of H consisting of vectors of norm 1 such that the Hilbert space H is a Hilbert sum for X ranging over all of E of the closure of the subspace generated by X moved around by all the pi of A for A ranging over your sister algebra. So in other words, you pick an X in E, you form a set of vectors of the form pi of A times X for X A ranging over your sister algebra. That's easily checked to be a subspace. You close it so that now it becomes a Hilbert subspace. And I claim that if you look at different X's in your set E, then you're going to get orthogonal subspaces, and you can add them up all to the entire Hilbert space. Moreover, as can be more or less seen immediately here, if you pick A in your sister algebra, pi of A leaves each of those summands in this sum stable, so it maps that summand to itself. And so in other words, you could write pi of A as a sort of diagonal action, which really acts on each of those summands separately. That's a complete description of our representation, because if you pay attention, you could define a representation of your sister algebra on each summand, because indeed each summand is left stable by the action of pi of A for any A in your sister algebra. And of course, the resulting representation is cyclic, with a cyclic vector given by this vector X in the set E corresponding to that particular summand. So let's prove this result. It's really, again, a Zorn maximality result. So let script E be the set of all subset E of my Hilbert space H, consisting only of normalized vectors, with the additional property that if psi and eta are two distinct vectors in E, then the subspace pi of A times psi for A ranging over the sister algebra is orthogonal to the subspace pi of A times eta for A ranging again over your whole sister algebra. So the set script E is not empty because it contains all the singleton consisting of a single normalized vector. So it's a non-empty set. It's ordered by inclusion, and it's fairly easy to check that actually it satisfies the hypothesis of Zorn's lemma. Indeed, if you take a linearly ordered collection of such subsets, the upper bound is obtained by simply taking the union. Therefore, script E has a maximal element. Let's call that maximal element E again. It has the property listed in the displayed equation. Let's suppose that the Hilbert space H is not equal to the sum for all the X's in E of these subspaces that we have arranged to be orthogonal by definition of E. So well, that means that there must be some vector that is orthogonal to that direct sum and is non-zero. Then let X be any element in E, and let's calculate pi of A times X inner product with pi of B times Y, where A and B are arbitrary elements in my sister algebra. Using the fact that pi is a star morphism and the definition of the adjoint, this is equal to the inner product of pi of AB star at X with Y. But what do I know about Y? Well, Y is orthogonal to, in particular, pi of AB star at X by construction. So that inner product is 0. So what this is saying is that if you look at the space of all the vectors of the form pi of B applied to Y for B ranging over the entire sister algebra, this whole space is orthogonal to the space pi of A times X, where A ranges over your whole sister algebra. And X was arbitrary in E. So what this tells you is that Y would be added to E, and we still would have the properties that is displayed above. And that contradicts maximality of E. So the proof is done. So this theorem says that any star representation is essentially obtained as a sum, properly defined, the theorem tells you what it means, of cyclic representations, or in other words, up to unitary equivalence, it is really a sum of GNS representation. I want to conclude my lecture with a note on irreducibility, because a natural question that may arise is, are those cyclic representations in some fundamental sense irreducible? Are they the smallest representation in some sense? The answer is no. The notion of a star representation being irreducible is well defined. A star representation pi of a C-star algebra is irreducible if the following property holds. If you find a closed subspace M of your Hilbert space with the property that for any A new C-star algebra, pi of A of M is a subset of M, then M must be the singleton 0, or M must be the entire Hilbert space. That notion of irreducibility can be rephrased in many ways. So for instance, you could say that the only projection that commute with all of the pi of A for A ranging over the whole system algebra are either the trivial 0 projection or the identity. So in particular, irreducible representations are always cyclic, right? Because if you pick a vector that's non-zero in your Hilbert space and you apply to it pi of A for A ranging over all the system algebra, then you get a subspace, you can close it, you get a closed subspace, and if it's not zero, which it isn't if you started from the non-zero vector, since pi will map the identity 1 to the identity, then you get that it's a whole space. So this any vector that is non-zero in your Hilbert space is cyclic for an irreducible representation. And so you could ask, well, are the states associated to these cyclic vectors for irreducible representation special? And yes, they call the pure states, and actually, and very interestingly, they are the extreme point of the state space. So there are some interesting topological connections going on there. If you look at what an irreducible representation of a abelian system algebra is, well, you will actually prove that they are the characters. They must be one-dimensional. It's very easy to check, and therefore they're the characters. So irreducible representations could be seen as generalization of the characters, or alternatively, pure states could be seen as generalization of characters. Those are certainly point of views that have been adopted in the literature occasionally, but arguably they are not particularly helpful, I would argue. In practice, the topological nature of, say, for instance, the pure state space inside the state space can be quite nasty. There are situations where the pure state space is actually dense in the weak star topology inside the whole of the state space. So because of that, the pure state space in particular, the set of all pure states of an arbitrary non-commutative system algebra, is by no means weak star compact in general. So owing to this, these replacements are not particularly nice. Another problem is if you work with irreducible representations is what topology to put on that sort of space. And while there are some really interesting and intriguing ideas, and while you can certainly get a lot of tractions working with the idea that representations are in some sense giving you a sort of spectrum, irreducible representations would be sort of the point in that spectrum. And you could be led to some ideas like Morita equivalence between system algebra, as the work of Mark Riffle on this topic shows. You can really get some interesting stuff going. Nonetheless, it would be a bit of a stretch to go as far as saying that irreducible representations, or for that matter pure states, are good replacement for points in non-commutative geometry. I think this statement is incorrect. I will now conclude this lecture on representation theory for system algebra.